My name is Jayla Međedović, and I am an author of algorithms and data structures for massive datasets. Um, so, yeah. So, my co-authors are Emin Tahirović and Ines Dedović. So I'll just first begin by saying a couple of things about every one of us. Emin and I actually both work at a university. We're both university professors. Emin got his PhD at UPenn in biostatistics. So he was kind of a choice of a co-author for the book because he has this probability and statistics expertise, which is really relevant for a lot of the succinct and probabilistic data structures. And Ines has a PhD in electrical engineering at University of Aachen. And actually, Ines is an illustrator for our book, and it's a very lucky coincidence that she also has the technical expertise, so it's much easier to communicate the technical ideas to an illustrator who also knows technical stuff. I'm a professor at International University of Sarajevo. I got my PhD in the US at Stony Brook University. And my PhD was exactly on algorithms and data structures for massive data sets, external memory algorithms, succinct data structures, and so on. And actually, part of the motivation for writing this book came from having returned to my home country, Bosnia-Herzegovina, and teaching a course on these subjects and realizing that there's no really one book that I could recommend to my students to study from. And there is a lot of material. There's a lot of research papers on these subjects. There's a lot of blog posts on the other end of the spectrum, blog posts by in industry. But I felt but it's all kind of scattered all over the internet. And I felt like there is a need for books such as this one. So here is a brief table of contents of our book, and basically it consists of three main parts. First part is hash-based sketches, which talks about what happens when data structures that you're used to using cannot fit into RAM, right? So it's kind of an implicit assumption when you're learning about data structures and algorithms that everything can fit into RAM, and then you're optimizing the computation. So when that is not the case, and that is very frequently now not the case, then there is this whole mini toolbox of data structures that you can use that are basically like approximate description and signature of data that is not always correct, but the error is so low and it's tunable that basically it pays off much more to hold this kind of a data structure in RAM than to have to go to disk. Second part is related to real-time analytics, streaming data, the context of streaming, sampling, quantiles, histograms. Basically, a streaming context is a very challenging one because all algorithms kind of have to be just a single scan and a lot of other things, and you have very little memory. So given those conditions, what's the best you can do? Like a lot of times you can't really perfectly solve a problem and get a completely correct answer in that kind of setup. So what is the best you can do? And the third part has to do with data structures for databases and external memory algorithms. So basically, whatever kind of database you're using, it is nowadays the database engines are optimized usually for particular workloads. So depending on what kind of application you're working with, you're building, this kind of learning about what data structures live underneath these engines will help you make a better choice of the right database engine for you. So something you might have concluded from what I've just mentioned is that this book is a little bit of a more advanced algorithms book, meaning it kind of assumes that you have gone through the course of regular algorithms and data structures, and in fact it builds on that material, right? So for example, you must have learned about merge sort, and then you will learn about how merge sort works in external memory and stuff like that. One of the main themes of the book is this trade-off between space and accuracy, right? A lot of times you don't have enough space to store a lot of data, so you have to sacrifice the accuracy to win when it comes to space. So that's one of the kind of main conflicts that we illustrate in this book. Alrighty, so today I want to talk about hashing. Hopefully there's going to be more chance to talk about, other topics from the book, because hashing is something that, is actually a classical data structure, something you must have learned about, if you're a software developer, either you know about it explicitly or you're using it, but you don't know that you're using it. And so the question is, why did I decide to talk about hashing today? It's actually chapter 2 of our book. And there's two reasons for that. One reason is that hashing is a backbone for all the succinct data structures in part 1 that we talk about. So on one hand, it's kind of good to know hashing starting this book, because it's a good review for the chapters to come. However, hash tables have also over time been adapted to serve in these massive distributed systems. And today we're going to look at one algorithm that is for distributed hashing, which is called consistent hashing. So as an outline of today, I would say first we will do some basic review of hashing. What are some applications? How do you resolve collisions? And how some modern programming languages implement hash tables. Because on one hand, if you're a researcher in algorithms, you see research on hashing, and you see a lot of these kind of theoretical things going on. However, in practice, there's kind of a different thing that you often want to optimize. So we'll talk about this this combination and this kind of a theory versus practice type of thing. And in the second half of the talk, I'm going to speak about consistent hashing. Alrighty, so hashing is everywhere, and pretty much it's easier to kind of find an application. It's much easier to find an application that uses hashing than the one that doesn't. If you just think of an example of how many times you use hashing while you send an email. First of all, when you log in, the password is hashed at the server and it's checked against the database to verify a match, right? So if there's a match, then you can log in. As you write an email, spell checker will hash words to check whether something is correctly spelled. When you send an email, each email is kind of split into little packets, and each packet on it carries a hash of an IP destination IP address. So if it's a non-existing hash, then the packet bounces. And then on the arriving side, when somebody receives your email, a spam filter might use hashing to check whether your email contains one of those spam-like words to kind of classify it as spam. And pretty much with pretty much anything, I could give you an example of hashing being used in pretty much every application at least 2 or 3 times. One of the applications, kind of more modern applications when it comes to big data and dealing with large data sets, is deduplication. Deduplication is something, basically it's the process of removing duplicates. And it's especially important in these storage backup systems such as, I don't know, Dropbox or Data Domain and applications like that. So basically what happens there is, if you're working for a company like that, then you might have very big clients, like enterprise clients, and you might have a contract with them where you are taking backups of their data. So if between 2 consecutive snapshots of data, let's say between every 24 hours, you might notice that most of the content, like 99% or more of the content, is actually identical, right? People modify some files, but between, in a short time span, not much changes. And basically what they do is they're saying, well, we're not going to store the whole, all of the data every new time again. First of all, that takes a lot of bandwidth. And second of all, that takes a lot of space. And it's just not a smart thing to do. So what they do is, when they're getting new files, is they use hashing to quickly identify what they already have. So for example, one such system is called chunk stash. And so when a new file arrives, it's split into these little chunks, and you might decide how big of a chunk you want to have. The smaller the chunk, the finer the granularity of your deduplication. And every chunk is hashed, right? So every chunk has a little hash associated with it. And for each of those hashes, you go to hash table and check whether you already have it. And if you don't have it, then the new chunk and the chunk ID are added both to the storage and to the hash table. However, if you already have a chunk ID, then you just say, okay, this is a duplicate. We're not going to store this. So this is a kind of a very common thing that's done nowadays in systems like that. And this process has to be really fast. You need to be really quick at figuring out whether you need a new chunk or not. Many other applications of hashing, like string matching, exactly, Git uses something similar. Yeah, a lot of other applications use kind of an exactly, the duplication is there, is kind of everywhere as well, not just in these storage backup systems. And actually something that was shown to be at some point vulnerability is it happened to users at some point, from what I understand, is that they tried to upload like a huge file that would normally need a lot of time to upload, and they would notice that they would immediately get the message that it's uploaded. So that's kind of a security vulnerability that I think was fixed at some point, because it would let you know that somebody else has the same file. And if you have these little chunks, then that's sensitive to small edits of the file as well. So the duplication is really, there's a lot of work on optimizing the duplication process at many places. And actually in this deduplication, a string matching algorithm, a string hashing algorithm is used, which is Karp-Rabin fingerprinting. And this is one of the fastest string matching algorithms. And part of the reason for that is that it uses hashing, right? So instead of comparing substrings, actual substrings, it compares hashes of substrings. But I'm not going to go into more detail about that. You might already be familiar with Karp-Rabin. It's kind of a randomized, really fast string matching algorithm. So you might be thinking why we love hash tables so much, right? Well, first of all, in short, it seems like a kind of a perfect dictionary. And why do I say perfect? Well, when you look at these other data structures like arrays and linked lists and binary search trees, hash tables are the only one that run in constant time when it comes to lookup, insert, and delete. And so that's where the perfect comes from. However, where does the illusion come from? Well, it's only expected, right? So it doesn't offer the kind of guarantee that a binary search tree offers, that, you know, operations will not run longer than logarithmic time. So in hash tables, the worst case is linear time, which is pretty terrible. And the reason for that is because many items might map to the same hash bucket, which kind of turns your search into a linear kind of search. However, this worst case linear time is not as bad as you would say that, let's say, unsorted arrays have a linear time search. Right, that's also true, but that's not the same worst case linear time, because in the case of arrays, that worst case will happen very consistently. Actually, every time you look for something that's not in the array, you will get linear time. However, with hash tables, if you have a pretty good hash function, it will happen almost never. So it doesn't offer guarantees that are constant time. Some versions of hash tables do, but interestingly, those are almost never implemented in real life because they complicate the common case. And we'll see more about the importance of common case in hash tables. So a lot of things depend on how good of a hash function you have. And as somebody who comes from academia, thank you, Ibrahim Begovic. So there's a kind of a ton of literature on hash functions, and there's a lot of complicated math also in relation to hash function. But the main thing to know about it is that what hash function does, basically, like a word is the same source as hash brown, so it kind of minces and chops data into little pieces until the point when whatever the original data was is unrecognizable. And there's a lot of research on cryptographic hash functions, right? So how do you send something? How do you hash something so that nobody can figure out what is it that you hashed? However, for the purposes of what we're talking about and massive data structures, we want much less from hash functions. We want simple and fast and easy to evaluate hash functions, and we want the hash functions that distribute data well in common cases, right? One of the examples is that of a set of hash functions that gained a lot of popularity is murmur hash, originally invented by Austin Appleby. And I just want to show a little example here of murmur hash, one of the wrappers of MMH3. And here you have a function a method hash and hash 64 and hash 128, depending on how long hash you want to have. And you can set the seed, whether you want a signed or unsigned integer, or even what kind of architecture you have. And the name of murmur hash came from multiply plus rotate, which are the main things that main ways to chop and mince data in this function. So that's kind of murmur hash has been used a lot in these kind of succinct data structures. But whichever way you look at it, hash functions are bound to introduce collisions. And that's because you're mapping a huge universe of potential items to a much smaller set of hash table buckets, right? So just by simple logic or pigeonhole principle, if you want to be mathematical about it, you will always have some items going to the same bucket. So that's kind of a bad situation. And to do that and to solve that problem, we have different collision resolution techniques. And I'm kind of assuming people mostly know about these, so I'm not going to explain them too much. I'm just showing two basic ones, chaining and linear probing, where chaining associates a linear linked list with each bucket. So all the items that hash to a particular bucket are stored in one list. For example, here in position 3, you have B, D, and A. And once something again hashes to 3, like C does here, it's inserted at the front of the chain. Now, linear probing, on the other hand, stores is a version of something called open addressing, and it stores item inside the slots. And if the position where you hashed is taken, then you search downward for the first available position to store an item. There are a lot more details to this, but for now, let's say this is enough. And people have researched about what's faster, what works better, right? And you have theorems saying that with high probability, these chains in the chaining table are going to be lengths in the worst case no longer than log n over log n, so some kind of a little bit less than logarithmic length. Whereas the consecutive runs in linear probing are going to be of length logarithmic, so a little bit longer. Why do we care about this? Well, clearly this length is what defines how long your search is going to be and how long your delete is going to be, and so on and so forth. And it kind of makes sense that the linear probing here has these longer runs, because different items from different buckets can participate in the same run, whereas in chaining, only the items from one bucket belong to a one linked list. So there's a lot of debate of what's better, and some methods, like I think C++ hash table unordered map uses chaining. I think even hash map in Java uses chaining, but there's a lot of criticism there as well, because chaining uses extra pointers, which is a lot of extra space. However, what's really a kind of an important detail that distinguishes linear probing is that all the items in linear probing are sequentially ordered in memory. So when you're fetching something, you're anyway fetching a whole cache line. So whether your run is, log n or log n over log n or 1 or 100, it matters a little less, because you're doing one memory access. Whereas in chaining, you might be doing many memory accesses because of the way linked lists are laid out in memory. So a lot of the production hash tables actually use linear probing. So for example, if we look at how Python implements hash tables, Python uses for their data structure dict, which is one of the most widely used Python data structures. It uses a hash table. And if you are unfamiliar with dict, I'll just briefly show an example. Let me know, whoever is online, have you used the dict? That's my question for you. Here's an example where no answers yet. Here I have a dictionary in Python, which is basically a set of key value pairs. You can't have duplicate. Sure, okay, this is what I expected. Cool. You can't have duplicate keys, but you can have duplicate values. And you have to use keys that are hashable, which means it cannot be mutable type. It cannot be a list. It can be an integer, a double, a tuple, a string, something like that. So here, if I run this Python dict example, you get that what the items are, what the keys are. Notice that in Python, hash of 5 is 5, so it's not a very mysterious hash function that's used, and so on and so forth. So Python dict actually uses open addressing, so it doesn't use chaining. However, it doesn't use linear probing, and it uses actually a different probe sequence to find the next position for the item if the current position is taken. And it's the following one as shown here. J is 5 times j plus 1 modulo the size of the table. So for example, if I have an item X that hashed 0 and the size of the table is 8, so I is 3, table size is 8, then the first j is going to be 0, right? But if 0 is taken, then I'm going to say 5 times 0 plus 1 modulo 8, that's 1. And if 1 is taken, I'm going to do 1 times 5 plus 1 modulo 8, that's 6. If 6 is taken, I'm going to do 5 times 6, 30, 31 modulo 8, 7, and so on and so forth. Why does Python use this and not linear probing? Well, their explanation, according to their documentation, is that it's all because they have a hash function that for integers is actually the integer itself. So hash of 153 is 153. And the reason why they do that is because a lot of times a very common case of insertion is going to be consecutive integers. So when you have consecutive integers, and their hashes are also consecutive integers, so they will fill up contiguous areas of the table, and they think that's very good because this is going to be a very fast sequential insertion of the types of data that they kind of get a lot. Like a very frequent case is getting just a sequence of sorted data or consecutive data. However, that creates a problem with collision resolution because you already have these long runs. You don't want to create even longer runs with linear probing, so they do this kind of probe sequence to break it up a little. And they add to what I just showed, they add a little perturb variable that allows you to also use higher bits of the item. Like if you look at this sequence, the same sequence would be followed by an item, by two items that are different but have the last I bits of their hash identical, right? So, and that's not very good because you're kind of not using all the bits. So they add a little thing to have the higher bits play some role as well. Now again, in this kind of situation, you also have a really bad case. Like if inserts exactly follow the pattern of 5j plus 1, then you're in trouble, right? Then you have to look for a really long time until you insert an item. However, what Python does, and what I think is a good kind of algorithmic engineering principle, is that what they want to do is kind of make the common case really fast. And if there's an occasional glitch, like if it just happens so that somebody has a data set that follows the 5j plus 1 pattern, well, then that's fine, right? We can tolerate an occasional glitch. And in a real system, something else is likely to go wrong anyway. So that might not be the worst of the problems. So this is kind of how Python, I think, in a way balances some of the theory, right? Because here you're bound to visit every position as you go on. So this is kind of some interesting math. And they're balancing something that is, optimizing the common case and trying to avoid the bad cases as much as they can. So that's about kind of classical hash tables and the first part of the talk. Are there any questions so far? comments or anything while I sip my coffee? Nope? Okay. Alrighty. So I guess the second half of the talk is maybe why a lot of people who are in the session maybe have joined, and that has to do with hash tables for massive data. So what has changed, right? What has changed? What changes when you have a hash table that stores a big data set? So a lot of things have changed, and there's research in various directions with respect to that. One is designing space-efficient hash tables. So, for example, if you can somehow engineer the space usage so that you save 1 bit per slot, just 1 bit in a large hash table, then you are probably saving gigabytes of space. Right, so there's a lot of work towards designing these really space-efficient hash tables with kind of various algorithmic tricks. So that's one thing. Another thing is now much more focus is placed on spatial locality that I was mentioning with respect to linear probing, where you're accessing things sequentially. So there's a lot of work in figuring out, well, okay, this collision resolution is good because the search has fewer probes, but where are the probes? Are they sequential? Can we turn a hash table into a data structure that exhibits a good spatial locality? This is especially the case if your data structure is on disk. And the last but not the least, and actually what will be the topic of the rest of our talk, is what happens if you spread a hash table across different machines. Well, first of all, when would you want to do that, right? There are a lot of situations in which you might want to do that, and one of them is, for example, web caching. So the setup being clients accessing web pages. However, you don't want to download the web page every new time from the original server, and you have caches sitting between clients and servers, and they are the ones serving the requests. So basically you have a whole network of caches, and every cache has some resources, right? Some web pages. Similarly, similar setup would be if you have a database and you have a cluster, right? So you want to distribute queries to different database servers so that you relieve some of these hotspots. And distributed hash tables are used by big companies, by distributed services. Discord is one of them, Amazon Dynamo, Akamai, Cord. A lot of people who have very busy services running on the web where they have caches serving requests, they are usually the ones that use distributed hash tables. So what's the setup, right? What's the setup of a distributed hashing, and what makes it different than why can't you just use a regular hash table at each particular node? Well, first of all, let me move this here. First of all, the setup is that you have a network of certain nodes, and every node features some resources, right? And resources are the local kind of hash table. And the important thing is for the client to know who has what, right? So if, let's say, I'm looking for resource number 14, whatever, it's important for me to know where to look for it, because resources are distributed along different nodes. And this mapping should be simple, it should be fast, and it should be so that no particular node is overloaded with requests. Now you could say that, you know, some web pages are accessed more than others and so on and so forth, and that's true, but for now let's just assume that every resource, every web page is kind of equally popular. So basically what you want to do is you want each node to have a fairly equal load, right? So these are the things I'm going to kind of emphasize at the bottom of this slide. So simple, fast mapping and equal load are two important things. And this, for now, looks like a typical hashing problem, because if you are given, let's say, m nodes and you have n resources, then you can create a hash table of m buckets, and each bucket would correspond to one of the nodes, right? So basically, I would just hash the resource that I have. Maybe it's a URL, maybe it's an IP address, maybe it can be a lot of things. So you hash it, and to whichever bucket it falls, then that should be the node containing the resource. So in this particular example, hashing R14 gave us 2, and node 2 actually contains R14. If it doesn't, it has to download it from the server. So yeah, this looks like it's classical hashing, right? However, one of the problems with these distributed systems, well, not problems, but, you know, features, is that nodes frequently come and go, right? So what happens is that you would have a spontaneous failure of a node, or you would have a new node joining the network and so on. So now a problem arises is, if my, let's say, cache number 2, node number 2 left, what am I going to do with the resources that used to be at this node? Or when a new node number 6 arrives, what am I going to, I should be able to give it some resources so it's not just sitting, you know, not doing anything. If we tried to, kind of, good afternoon, if we tried to, in a way, artificially fit this scenario to work with regular hash tables, what we would have to do is basically we would have to resize a hash table every time some node comes or leaves. So for example, a node 6 arrives, and what I need to do is I need to rehash the whole table, rehash all the elements, just to have one more bucket, right? I would have a hash function with a range that's by 1 bigger than the previous hash function. And the resizing of hash tables is commonly done. However, resizing a hash table is a linear time operation, and the only reason why it makes sense in normal hash tables is because it's, when you increase the hash table, you double it. So you know that for a while you won't have to do it all over again, right? Basically, this expensive step is amortized against a large number of really cheap operations. However, in this context that we have with nodes coming and leaving, what rehashing would mean is that all of these resources sitting at the nodes would now be, all the mappings would be out of date, right? So if I now rehashed, I don't know, R16 is not anymore at bucket 2, now it's at the bucket 4. And this is just not practical. You can't do this because it's a very dynamic setting, and you just don't have time to keep downloading new resources all over again. It would be a complete mess. So consistent hashing algorithm is something that addresses this problem. Basically, another way to, the word consistent should be a clue, because consistent means how do we add and take away buckets without disturbing all of the mappings, right? So that's the basic idea of consistent hashing. And the first paper that came out was in 1997. But ever since, it's been used in like a ton of other situations. Because the drawings are occluded by my camera. Let me try to move it to the other side. I hope this works. I hope this is gonna be okay now. Okay, good. So the basic idea of consistent hashing is this hash ring. And a hash ring is basically an interval. Here I have an interval 0 to 2 to the k minus 1. K is usually made big, like 32 or 63 or something like that, just so that this interval is large enough so that there's no collisions. And basically, the 0 of that interval is at the very top of this hash ring, and the rest of the interval is spread out uniformly clockwise around the ring. That's kind of visually the best way to imagine it. So in this example here that I have, by the way, all of these illustrations are from our book made by Ines, except from some of the ugly ones that I made that I'm sure you can tell a difference. So 0 to 31 is the hash ring that we have here. So k is 5. And basically, the idea behind the hash ring is to hash both nodes and the resources on the hash ring. So these little diamond shapes here are resources, and the little humans sitting at their desks are nodes, right? So every node and every resource have a position on the hash ring. So here is B hash to 2, so it's right here at the beginning of the hash ring, and on the other side, on the south side, we have E mapping to 16, and so on and so forth. So the way assignment of resources to bucket works now is really simple, and that is that every resource travels clockwise until they encounter the first node. So for example, A, which hashed to 28, would travel clockwise until 5. So 5 is the node responsible for the resource 28. Also, let's take an example of 10, D hash to 10. I'm conflating the resource ID and just the resource itself, so you'll forgive me for that. So 10 goes clockwise until 12, or 21 goes clockwise until 27. So this is the basic logic. Now, what's special about this? Well, for now, nothing in particular, except that the load should be fairly equal, because if you have a pretty good hash function, then nodes should fall kind of uniformly across circle, and so should resources. So you would expect no node to have too many resources or too few resources. However, the beauty of the method is that what happens if I add a new node? So a new node has just arrived. In this example, it's the node number 30. In that case, some of the resources that belong to node's successor 5 should now be reassigned to belong to 30, right? So A and Y now kind of encounter 30 sooner than they encounter 5. The nice thing about this is that the rest of the network remains unchanged. So only the mappings of one other node have been modified after this new node has arrived. And similarly, it's with when a node leaves, right? And node leaving happens a lot as well, because it's like a spontaneous failure of a node or something. So in that case, when a node quits, you see this little human here leaving, so like they've just quit or something. What happens there is that their resources need to be reassigned to whoever was the successor of the node that left. So now 18 should contain as resources not only 16, but also 7 and 10. And again, this only affects one node, right? So all the other mappings stay in place. And this is pretty cool. It's kind of simple, simple yet really cool. So if you're interested kind of to better understand how this stuff works, you might benefit from kind of implementing it yourself. Or what I'm going to show here and what we have in the book is a simple demo implementation of this kind of a hash ring functionality. I'm now again going to have to move and reduce my camera. I apologize for my camera getting in the way. I just noticed it. So if we look at this implementation here, basically the easiest way to have a simple implementation of a hash ring is to do a circular doubly linked list, right? So you have nodes, and every node contains its own hash value, and it contains a dictionary of resources. There's also, and the hash ring as a head node has the smallest node with the smallest value. So in our case, 5. If I go to here, 5 would be the head node, right? There's a lot of, I'm not going to explain all the details of this implementation. I'm just going to go through the basic logic of main methods and kind of run a little example. The important method is that of distance, which actually implements the clockwise ring distance from a resource to a node or from a node to another node. Keep in mind that here the order of parameters is really important. So distance from A to B is not the same as distance from B to A, right? It's actually the size of the interval minus the other. Again, a lot of the code here is basically the kind of code that you would need to implement a circular doubly linked list. So when you're looking up a node, basically you're starting from the head node, and the main kind of part that I'm selecting now tells you that basically you should be skipping over nodes. You should be advancing through the list until you're about to skip over the resource, right? So for example, my lookup, let's say I'm looking up who's the successor of 23. So I'm starting at the first node, which is 5, and as long as the node that comes after the current node has the smaller distance to my resource than me, I'm going to advance. So 5 is further away from 23 than 12 is, so I advance to 12. Same thing with 12 and 18. 18 is closer to 23 than 12 is. And now, actually, 18 is closer to 23 than 27 is to 23, because 27 goes all the way around. And that means that 27 is the successor of the resource. So that's kind of the logic of the lookup. If you want to add a new node, you again do all the mechanics of adding a node to a circular doubly linked list, except that what you also have to do is you have to verify whether there are resources that you might need to move from the node's successor to the new node itself. So if some of the resources have shorter distance to this new node, then move them otherwise, and delete them from the other node. So move resources method here is useful both when we are doing inserts and when we're doing deletes. And here's the simple print hash ring method. So now I'm just going to do a small example where I'm going to create a hash ring with k equal to 32. So 0 to 2 to the 32 minus 1 is the range of the interval. And I'm going to generate 100 random numbers that go up until, well, they're all in the range. They go up until 2 to the 15 minus 1. And I'm going to make sure they're all different, because my implementation assumes that all nodes have to have distinct values. And I'm going to add those nodes And then I'm going to add 300 resources in a similar fashion. And then I'm going to print the hash ring, hopefully just once. So let me see if I run this example here. What am I going to get? So here is my hash ring, which features 100 nodes, and we will not inspect everything right now, but basically the nodes are shown in the clockwise order, and every node shows the resources that they have. Okay, so for example, resource 66 belongs to node 93 because the node right before was 65, and so on and so forth. But notice that there's actually some nodes have more and some nodes have less, right? Some nodes are even empty and some nodes have about 10 resources. We inserted 300 resources and 100 nodes, so you would expect kind of 3 on average per node. But you can see that there's actually quite a lot of variation. And this is something that will consistently happen, right? We do expect things to be roughly equal, but oh, sorry, I totally missed some comments. Hi, Tarek Pasic. I don't have those enabled. Thanks. Cool. So yeah, so now what we can do is we can, for example, I can choose to delete the node. I don't know. I can choose to delete this node 28346. Just kind of to show 28346. Actually, no, because I'm going to have to run the whole random process again, so I might not have that node. So I'm just going to remove a node that is in some position, let's say, of the list. I don't know, I'm just kind of playing. Let's see what happens. So now it again prints. Actually, I'm going to try to not print it again. I just want to show the effect of removing a node. So see, when I remove a node, I'm removing the node with ID 17191, and it's actually going to remove all of its resources to whatever is the successor. If we went and checked, we would actually see that this is the successor of the node. But as I mentioned, notice that this is not a very even distribution of resources, and that can in fact be quite a problem. And actually many companies that use consistent hashing, they do make certain optimizations here. And also notice that what I've shown as a demo implementation uses this linked list linear time lookup. And that's not, notice that, you know, in a big network, that's a very expensive operation. So there's something called finger tables. That is used in the place of kind of uses a little bit more space per node, but actually it allows you to do a faster logarithmic lookup. So for example, a finger table here that is built at the node 5, what it does is basically it records kind of, it hardwires in the node who are the successors of certain points on the hash ring. And those points are at exponentially increasing distances from 5. So 6 and 7 and 9 and 13 and 21 and so on and so forth. So the finger table will basically, every time it you multiply the distance by 2. So basically this finger table is going to have a logarithmic number of entries. And you're going to pre-compute who the successors are of these points. So for example, 6, 7, and 9 all have 12 as a successor. 13 has 16 as a successor, and 21 has 27 as a successor. So this kind of table, if you build it at every node, it can really help you do a faster lookup. So for example, let's say you're looking up at a resource A whose hash is 29 and you're starting here. Let's say that's where the request arrived. So what you need to do is you need to take the largest kind of finger, the furthest away that is still comes before 29. In this case, this is 21. So we go to the successor of 21, which is 27. And to get to 29, we need 2. And it actually just happens that 29 we exactly have that successor recorded there at 30. There's a small mistake here. 27 plus 16, successor is not 5, it's 12, but never mind. So this ensures a logarithmic lookup. So that's one optimization you can do. Another optimization you can do has to do with what I showed in demo implementation, where you have you can very easily get a varying number of resources per node, especially if you are kind of you do a couple of deletes of nodes, right? So you end up getting a node, for example, here, you're gonna end up getting 18 being responsible for a pretty big part of the circle or hash ring, right? So now you're even more likely to get more resources, and it's kind of a perpetuating problem. So as the network changes, it can easily deform to have just one node address a lot of requests. And one way to help with that is to actually do something called virtual nodes, where you have the exact copy of the same node thrown along the hash ring. And you do that with all of the nodes. Sometimes that's done when you have one server that has more capacity. So let's say if a server has twice the capacity of all the other servers, then you want to map it twice on the hash ring so that it receives twice as many requests. So I believe something like that is done in Amazon Dynamo. All right, so that's it when it comes to finger tables and when it comes to consistent hashing. I hope this session has been at least somewhat enlightening with respect to hash tables in general and hash tables for massive data sets. I guess let me see if people are, if you have any questions at this point or anything like that, I would be happy to address them. Hashing is a huge subject, so definitely it kind of deserves a book of its own. I hope that at some point, again, we will have an opportunity, or maybe one of my co-authors, to present some of the data structures that we actually introduce in this book. The book is already in MEEP, in the early access program, and so far we have about half of the book already posted online as the ebook. And because it's a working version, we really welcome the feedback, and we have benefited from readers' feedback in the past. So please do make comments on the live book. It's really helpful, and it's great to get feedback, as you know yourself. Yep. So we have first 5 chapters posted, and soon there will be 6 and 7 posted as well. And by the end of summer, we plan the book to be finished. And so, yeah, we're very excited about that. Anyway, okay, that's it for me. Where is it posted? The book. So if you go to, I guess what I can send you is, and I can actually do that right now. I can now send you the link, if that's the question. I believe here's the link for the book. There's also some free content. I know that some of the chapters have been turned into articles. You're welcome. Like bloom filters, and also some of the other things will be. Yep. Alrighty. Okay. Thank you for watching this session, and please let me know what you think. As I said, we welcome all kinds of feedback. Thanks a lot. Bye bye.